Newton's law of cooling is a special type of differential equation. Okay? When an object is cooling, the rate at which the temperature drops is proportional to the temperature difference between the object and its surroundings. Okay? Meaning, on a map of the world, if I've got Australia here, and I've got a cup of coffee whose initial temperature is 90 degrees, and the temperature around me is 25 degrees, compared to if I'm down here in Antarctica with a cup of coffee, again, initial temperature 90 degrees, ambient temperature or the temperature of the surroundings could be minus 5 degrees. Okay, the difference between these two is 75 degrees. The difference between these two, 95 degrees. Because there's a bigger difference here between the temperature of the coffee and the temperature of the surroundings, in Antarctica our coffee is going to get colder quicker, which is basically what this rule is saying. Okay, and that's what we know to be intuitively true in any case. Okay, so the way we write this as a differential equation is the rate at which the temperature is changing with respect to the time is some constant multiplied by the difference between the temperature of the liquid or the object and the ambient temperature. So just to define a few things, TA is the ambient temperature. Okay, sometimes also written as the room temperature. And T0 is the initial temperature, okay, of the object. So I need to somehow find some formula for the temperature, okay, as a function of the time. Okay, that's my goal. The way I'm going to do this is using separation of variables. Okay, so I'm going to start by multiplying by dt. So k t minus ta dt. Okay, from here I can't integrate both sides yet because I've still got that capital T there. So I'm going to divide both sides by t minus ta. So dt on t minus ta, the ambient temperature, equals k dt. And now I'll integrate both sides. Integral of dt on t minus ta is the integral k dt. Okay, remember there's really a 1 implied in here. Okay, what I have is some function on the bottom, t minus ta. If I was to differentiate this with respect to t, ta is just a constant. Okay, the derivative would be 1, okay, because there's a 1 outside of the t here. So what I really have is one of these scenarios where I've got in here some function, in this case a function of capital T, and on the top its derivative, okay, integrating with respect to t. So the integral will be natural log of that function. Okay, so what all this is going to come down to is on the left hand side natural log of the denominator, and on the right hand side integrating a constant with respect to t. Again, integrating 3 dt would be 3t plus c, so over here it would be kt plus c. Okay, from here I can convert this into a log statement, so correction, an index statement. Natural log means log of base e, so I know that t minus ta will be e to the power kt plus c. Try to get capital T, the temperature, by itself. Should have defined these up here as well. Let T be the temperature, okay, and let little t be the time. Okay, just am I rearranging e to the power kt plus c plus ta. So I've essentially got t by itself. K is okay because that's like the rate at which it's decreasing. This plus c I don't really like. I'm going to try and get rid of it. So e to the power kt times e to the power c. Okay, because these are multiplied. I'll add the powers, add these powers, and end up with what I had there. I'm just undoing those index laws plus ta. Alright, so I want to try and find the value of EC. I'll just go to the aside. Okay, I know the initial temperature. When at the very start, the temperature will be the initial temperature. So I'll sub these in. E to the power k times 0 times e to the power c plus dA. Okay, and I'll try and get e to the power c by itself. So subtract ta from both sides. E power k times 0. That's just 0. I can simplify that in this line. I know anything to the power 0 is 1. So e to the power c is t0 minus ta. Okay, so I can now replace this. I can replace this e to the power c, okay, with that value. Okay, so e to the power kt t0 minus ta plus ta. And just to make it look pretty, I'll put the t0 minus ta in front. Okay, so this little step here is explained over here. Alright, so what we should highlight on here is this key result. If I have the temperature d time equals k t minus ta, I can write down this sort of equation. It'll always work out like that. You won't need to solve these from scratch. So you're allowed to skip all of those intermediate steps. Alright, let's have a look at a problem and see how it actually works out. Okay, Robin heats water to 70 degrees. He waits 10 minutes. What would be the temperature if K equals 0.056 and surrounding temperature is 27 degrees? Okay, so I identify it's a Newton's law of cooling problem. Okay, I'll write my relationship and my general one. Okay, I know that K equals 0.056 and I know the ambient temperature or the surrounding temperature is 27 degrees. So dt equals 0.056 t minus 27. Okay, I know from all that hard work I did, I can transform this sort of an equation, okay, into one of these. Alright, so I also know that the initial temperature is 70 degrees, so I can convert this. Okay, my formula for temperature will be 70 minus 27 e to the power 0.056 t plus 27. Okay, now that I've found that formula, I can sub in t equals 10 and to find what the temperature would be. Okay, and calculate an exercise from here. I made a small error here because the ambient temperature is less than the initial temperature. It's going to be cooling all the time. So since my K value is 0.056, it should really be a negative in here. Okay, and a negative there, and a negative there to show that it's decreasing. Okay, similar to those other differential equations. So with the negative in there, I get 51.56 degrees. and I'd write write some sentence about that. Okay, so always remember the k value is negative when it's decreasing. In some other textbooks, they'll have a negative here all the time, okay, but we just have a positive there, and it'll give us negative k values appropriately. Okay, we can solve all sorts of problems here. Here's another one. This one's in degrees Fahrenheit, but we can still use the same model. A 200 degree Fahrenheit cup of tea is left in a 65 degree room. At time t equals 0, the tea is cooling at 5 degrees per minute. What's the temperature of the tea after 10 minutes? Let's write down a few things we know. So I know that the initial temperature is 200 degrees. I know the ambient temperature is 65 degrees. Okay, and I know that the rate of change of temperature when t equals 0 equals 5 degrees per minute. Yeah, I'll identify that this is a Newton's law of cooling problem. So I'll write down my general relationship. dt equals kt minus ta. Okay, my goal here. Okay, I almost made the same mistake again. Okay, remember the rate of change is going to be negative because the cup of tea is cooling. Okay, so from this original equation, I can actually find the k value with the information I'm given at the moment. So I know initially this rate of change is minus 5. Okay, there's a k value which I'll be able to find. Okay, and at that initial time, the temperature was 200 and the ambient temperature is 65. So my k value will be minus 5 on 200 minus 65. Okay, and I should be able to find some simpler fractional representation of this. Okay, no fractions for me. And minus 1 on 27, that's better. Okay, so when I go to convert this Newton's law of cooling problem into a normal equation, okay, remember the normal rule. Alright, I can fill in all of these gaps now. So my initial temperature is 200, my ambient temperature is 65, e to the power -1 on 27 T plus 65 degrees. Okay, from now I can answer the question, what is the temperature of the tea after 10 minutes? Okay, I'll sub in T equals 10. Okay, and find what the temperature will be. Okay, just calculate a work from here. And up with 158.21 degrees. 158.21 degrees Fahrenheit. And I'll write some sentence about that. So just before we finish, if I was to graph this thing, it essentially start at 200 degrees and never get cooler than 65. So look at that horizontal asymptote going through. Okay, essentially looking like this. Exponential decay, but never getting cooler than 65. Okay, so from here, you have a go at all of these sorts of problems. Okay, lots of coffee cup problems, and there's some other problems from a worksheet I found online. Okay, you might be interested in this one, a bit more interesting application using the temperature of a dead corpse. Alright, good luck, see ya.